Hey, welcome back to Fat Mama Physics. In this video, we are going to continue on with gravitational fields. In the previous videos, we looked at gravitational potential energy of orbiting satellites. Now we're going to look at examples involving gravitational potential. So again, a lot of similarities with electric potential, and kind of think of it as the different points in elevation on, say, the fabric of space-time. Notice if you have, for a fabric of space-time, if you have a heavy object, it's going to cause a dip in the fabric. And the different, you can see the lines that kind of show where the height of the dip is about the same. That's showing you that the gravitational potential at that point is about the same. Okay, so then if you're going up from the bottom of the hill, your gravitational potential goes higher and higher and higher and higher relative to that dip. So that's your gravitational potential. The slope of the dip, so the steeper the slope, the stronger the gravitational field. The less steep, the shallower the dip, the lower the gravitational field. So all of these concepts go hand in hand with the concepts of electric field and electric potential. And the equations kind of show a lot of similarity as well. The only difference is that for gravitation, the masses only attract. They don't repel like charges do for electrostatics. So here we have an example. We have two big masses, and we want to find the gravitational potential at P. So hopefully you know this already. Here we have the gravitational potential that is due to a mass. So some distance away from a mass, you'll get a gravitational potential of big G, big M over R from the center, of course. And notice it looks very similar to the electric potential, which is KQ over R. Okay, so notice the similarities here. Okay, so some chicken scratch. Sorry about that. Let's do these calculations. Okay, so we have two masses, which means to find the gravitational potential at P, we need to add them up. And this is not a vector, so we just have to substitute in the mass and just sum them up like you would do like anything else. So the gravitational potential, which I'll label as Vg here, this is going to be, so we have two masses. I'll just call this guy green, I'll call this guy orange. Okay, so this will be equal to the green guy, the Vg of the green guy, plus the Vg, the gravitational potential of the orange guy. So this is going to be negative big G M of the green over the distance of separation, which is given there in the question very conveniently, and we just add up with the other one, with O. Okay, and I should probably label this as G and label this as O. Okay, substituting everything in, and this is nothing tricky here. Negative 6.67 times 10 to the power of negative 11. Mass there, some big number, 4.4 times 10 to the power of 12. Foregoing the units due to the small space here, 3.5 times 10 to the power of 5, and minus 6.67 times 10 to the power of negative 11 times 6.2 times 10 to the power of 10 over 2 times 10 to the power of 5. Phew! That's just a lot of numbers. It's not very difficult math, or just even conceptually either. Yeah, I didn't even bother putting in negative signs. I just added them positively and just slapped the negative at the end. So I get negative 8.59 times 10 to the power of negative 4. And this is going to be joule per kilogram. In which so that's the, by definition, the amount of work done per unit mass, moving that object of mass from that point, from infinity to that point closer to that point from both masses here in this case. So this amount of joules acting per unit of mass, which then rounding this up to about 2 sig figs, this is going to be negative 8.6 times 10 to the power of negative 4 joule per kilogram. Okay? All right. There's our first example. And then B, calculate the work needed to move this, to move a 100 kilogram person from P to infinity. Okay? So we know that the amount of work done, very similar to electric potential, is equal to the change in gravitational potential times the amount of mass that you're moving. Meaning, the more mass of the person you're trying to move, the more work you have to do. The larger the gravitational potential drop, or the difference, meaning you also have to put in more work to do that. So imagine moving a really heavy person, a really large person, up a very, up to Mount Everest kind of thing. That's the idea. A large potential difference is going to cost you a lot of work to do. That's why the relationship as you see there. So we know the gravitational potential, which is given here in this question. I'm not going to erase from my calculator. And because it is to infinity, at infinity, the gravitational potential is 0. Okay, just like how we set the reference point for gravitational potential energy to be 0 in infinity, same thing electric field, and notice this concept comes back again. So essentially, the change in gravitational potential is just this number that we got in the previous question. So I'm going to use the full blown out number, which is 8.59, without any rounding, times 10 to the power of negative 4. This is joules per kilogram, okay? And the reason why I'm using it as a positive number is because the change is going to be essentially 0 is my final, okay? Final minus initial minus this negative number is going to give you a positive number. And think of it this way. If I have to move a mass farther away from another attractive mass, hence fat mama physics, then I definitely need to do positive work. I'm increasing the energy of the system. So positive work has to be done. There's no way this should be negative at all. So hence me not putting in any negative sign since I'm using the previous number from the previous question. Okay, so the mass of this person is 100 kilograms, and the units cancel out nicely. Kilograms cancel out. So then after I multiply the 2, this is just 2 decimal places. And hence, this would mean this negative 4 gets changed up to a negative 2, and my number is essentially the same. 8.6 times 10 to the power of negative 2 joules to move this person from that point to infinity. Positive work needs to be done. So notice that for gravitational potential, masses always attract, meaning if you pull them further away, you're always increasing the electropotential energy between the two. Okay, so there we go. That is example 6 from 10.1 describing fields, gravitational potential, gravitational fields. Thank you for watching. Fat Mama Physics signing out.